Hi folks, we're going to take a look at page 179, number 5, an example of using implicit differentiation. So what they do is they give us this equation, which they tell us is the equation of an ellipse, and they want us to find the derivative at the point 1, -1, and then 2 points where the tangent is horizontal. So a couple of things here. In part A, they've actually done us a favor by giving us the y value at the given x value, so we don't actually have to go find that, since it's likely that the derivative will have the y variable included in it. And then in B, 2 points where the tangent is horizontal, think about the shape of an ellipse. Not surprising that you would have 2 places where the tangent is horizontal. Okay, so step 1 is to find the derivative, so we do that by taking the derivative of both sides of the equation. So derivative of the left here, so derivative of 5x squared is just 5 times the derivative of x squared, so 2x, so 5 times 2x is 10x. Okay, then here minus 6, and the derivative of xy, well, this is a product of 2 functions of x, so we need to use the product rule. Okay, so first derivative of the first, which is 1, times the second function, plus the first function, times the derivative of the second function. So that just leaves us with the dy dx, which I'm going to use prime notation to denote. Okay, so now we can go to the next part. So plus 5 times the derivative of y squared. This is where we're going to have to use the chain rule, since we have y is a function of x, and then that is being squared, so it's a composite function. So first we take the derivative of y squared with respect to y, so 2y, times the derivative of y with respect to x, which I'm going to denote y prime. Okay, and on the other side, well, the derivative of a constant is always equal to 0. So now that we've taken the derivative of both sides, our next step is to isolate y prime on one side of the equation. Okay, so I'll keep on this side the 10y y prime from this expression here. So 10y y prime, and then here I've got the negative 6 times xy prime, so minus 6xy prime. Okay, so just set it up so I have the subtraction afterwards, and we're going to take the other 2 expressions and bring them to the other side of the equation. It's those that don't have y prime. So we've got here the minus 6y, so bring it to the other side, 6y, and then here the 10x, so to the other side, minus 10x. Okay, and then here we would just factor out the y prime and divide the rest to the other side of the equation. So we're left with y prime, 6y minus 10x, and divide that by 10y minus 6x. Okay, and then let's just simplify that by factoring out a 2 from both numerator and denominator. Okay, so in the numerator we're left with 3y minus 5x, and denominator 5y minus 3x. And of course, the 2's that we factor out just reduce themselves to 1. Okay, so we have the derivative. Not surprisingly, it does include both x and y variables, so now we can go ahead and calculate the derivative at 1, -1. So I'll just remind you of some notation that I've used. So if I'm using Leibniz notation here, dy dx, I want to specify where I'm taking the derivative. You use this vertical line. Okay, so this says dy dx evaluated at, in this case here it's the point 1, -1, since I need both the x and y values and not just the x value. And now I can input that into the equation. So 3 times -1 minus 5 times 1 over 5 times -1 minus 3 times 1. Okay, and here we're left with -3 minus 5, -8 in the numerator, and here -5 minus 3, -8 in the denominator. Okay, so we're just left with 1. Now what you can do is you can always sketch this on Desmos and see that it indeed makes sense that the slope of the tangent at this point, 1, -1, is equal to 1. Okay, so let's go to part B. So here we want to know when the slope of the tangent is 0, since that's where the tangent will be horizontal. So we take our derivative, okay, and we set our derivative to 0. So we've got 0 equals 3y minus 5x over 5y minus 3x, and since this is a fraction, this fraction can only be equal to 0 when the numerator is equal to 0. So we have that 3y minus 5x has to be equal to 0. Okay, and what we can find is a relationship now between y and x. So y is going to have to be equal to, bring the 5x to the other side, so 5x, and divide by 3, so 5/3 x. So the derivative will be equal to 0 when y is equal to 5/3 x. So we need to determine when that happens, and so to do that we have to go back to the original equation. Okay, so we need to insert anywhere we see a 5 and y, we're going to replace that by 5/3 x and then solve for x. Okay, so here we have 5x squared, okay, minus 6xy. So we'll replace that by 5/3 x, and then we've got plus 5 times y squared, so 5/3 x squared, and all that is equal to 16. So let's now solve for x. Okay, so here we've got this just reduces to 2. So here we have 5x squared minus 2 times 5, 10x squared. So here we've got negative 5x squared. And here, a bit of work we got to do. So 5 times, so 25 over 9 x squared. Okay, equals 16. And here, well, we have 125 over 9. So let's put this to some fraction over 9. So that'll be negative 45 over 9 x squared plus 125 over 9 x squared equals 16. So here we have negative 45 plus 125 is 80. So 80 over 9 x squared equals 16. And so x squared is equal to 16 times 9 over 80. Okay, and now we have to take the square root of both sides. I'm not going to bother multiplying this out because I see these are both perfect squares, so I'm going to leave it as is. So here we have x is equal to, now remember we're taking a square root, so we have to consider that there's both a positive and negative possibility, and this fits into our assumption that we're going to have two possible answers here. In fact, they tell us there should be two. So here square root of 16, so 4 times square root of 9, which is 3, and 80, well, that's not perfect square, so we'll leave it as is. So we get x is equal to plus or minus 12 over root 80. Okay, now we have to solve for the y values at these x values because they ask us for the points. Now normally I would take these x values, put them back into the original equation for this relation, okay, and solve for y. However, in solving for when the derivative is 0, we actually had a relationship between y and x. We know that in order for this to occur, in other words, the derivative to be 0, we need y to be 5/3 x. So here we have a bit of a shortcut. We can determine the y values by just multiplying x by 5/3 x. Okay, and since it's just plus or minus, I think I can get this done in one step. So 5 over 3 times plus or minus 12 over root 80. Okay, so here that simplifies to 4. So we've got y equaling plus or minus 20 over root 80. Now this could be simplified by simplifying the square root, but I'm actually fine if we leave it as is. So our 2 points will be 12 over root 80 and 20 over root 80, and then our second point will be negative 12 over root 80 and negative 20 over root 80. Okay, and there we have it. So just to do a quick recap here, step number 1, finding the derivative by using implicit differentiation. So we had to use in that the product rule and the chain rule. Okay, From there, we were able to determine the derivative at a point by inputting the values that were given to us. And then in B, we had to determine when it was equal to 0. And that was just a matter of determining when that numerator was equal to 0. Okay, so that's it for this question.